Hello everyone, welcome to this lecture in the Neural Networks from Scratch series. In the previous lecture, we looked at backpropagation through a single neuron. In this lecture, our main objective is to look at backpropagation through multiple neurons or backpropagating through one layer. So, let me just provide a brief summary of the previous lecture. We took one neuron and which had three inputs, and each input had a weight associated with it. It had a ReLU activation function, and then the loss function was just the squared loss. The true value was 0. So our goal was to how to optimize the weights and biases of the neuron so that the output is close to 0. So for that we needed to find the gradient of the loss function with respect to W naught, with respect to W1 and W2, which are the three weights, and the gradient of loss with respect to the bias term. And the way to obtain that is to obtain the gradient of the loss with respect to W naught, you have to find the gradient of the loss with respect to the preceding unit, which is the ReLU. Then you have to find the gradient of ReLU with respect to the summation operation. Then the gradient of the summation with respect to X naught W naught. And then the gradient of X naught W naught with respect to W naught. So when you chain these four derivatives together through the chain rule, ultimately you obtain the derivative of loss with respect to W naught. And that's why it's called as backpropagation. We even saw how to do one pass of the backpropagation for each of the weights. So we calculated gradient of loss with W1, W2, W3 and W0. And we also calculated gradient of loss with respect to B. Finally, we showed one iteration of the gradient descent, and we showed that the new loss is 33.87, which is less than the earlier loss of 36. Then I took you to the Python code, and then I showed 200 iterations, and we showed that the loss almost decreased to 0, which means the weights and biases of the neural network or this single neuron were tuned so that we were close to the desired output value of 0. Now your question would be that, okay, this is fine for a single neuron, but the real power of neural networks comes from stacking these neurons together. So the real power of a neural network comes from multiple neurons or a layer. Today we are again going to look at backpropagation, but backpropagating through an entire layer of neurons. Similar to the previous lecture, I'll make this lecture extremely hands-on. We'll do everything from scratch. We'll even do a one iteration of gradient descent backpropagation on the whiteboard itself, and then I'll take you to the VS code, or we'll code in Python the 200 iterations. So let me explain the problem statement. We have four inputs here, and we have three neurons in the first hidden layer. If you see, each neuron has four weights associated with it. So if you look at the first neuron, the weights are denoted by the pink line, and they are W11, W12, W13 and W14, and the bias of the first neuron is B1. For the second neuron, it also has four weights associated with it, which are W21, W22, W23 and W24, and the bias associated with the second neuron is B2. The third neuron again has four weights associated with it, W31, W32, W33 and W34, and the bias associated with the third neuron is B3. Okay. Then the output of each of these neurons, the output of the first neuron is W11X1 plus W12X2 plus W13X3 plus W14X4 plus B1, that is passed through the ReLU, that leads to the answer of A1. The output of the second neuron, which is Z2, is passed through ReLU, which leads to an answer of A2. And the output of the third neuron, which is Z3, it is passed through ReLU, which leads to an answer of A3. And then finally, there is another neuron here which sums up these outputs, A1 plus A2 plus A3. And the loss is basically A1 plus A2 plus A3 minus 0, the whole square, which is essentially A1 plus A2 plus A3 whole square. So the true value of the output is equal to 0. So the question which we are asking indirectly is that, given this architecture, what are the best values of these 12 weights and these three biases so that the loss is as close to zero as possible. In other words, what are the values of the weights and biases so that A1 plus A2 plus A3 is very close to zero. So if you look at the number of parameters here, there are 12 weight parameters and 3 bias parameters. So overall there are 15 parameters to maximize in this case. And again I'm going to show you 15 parameters to optimize rather, not maximize. And again I'm going to show you how to optimize these parameters using the technique of backpropagation. So just a simple notation to start with. Whenever you are learning backpropagation, it's very important to use a clear notation of symbols. So I'm going to use Z1 as the output of the first neuron before going to its activation, A1 as the output after the ReLU activation, similarly Z2 and A2 and Z3 and A3. So A1 is ReLU of Z1, A2 is ReLU of Z2 and A3 is ReLU of Z3. The output of this final neuron here, A1 plus A2 plus A3, I'm going to call as Y. And so the loss, which is my final loss, is just equal to Y square, which is A1 plus A2 plus A3 whole square. So this is the notation which we are going to follow in today's lecture. Now, the whole idea of backpropagation is to find the gradient of the loss, which is obtained at this point, with respect to the weights here. Since we cannot find this directly, we first find the gradient of loss with respect to, remember this is y. We first find the gradient of loss with respect to y, then we find the gradient of y with respect to a1, then we find the gradient of a1 with respect to z1, and then we find the gradient of z1 with respect to, let's say, the first weight. Okay, now I want to focus on the first neuron. The first neuron has four weights: W11, W12, W13, and W14. First, I am going to find the gradient of loss with respect to W11, and I'm going to show you how to find this. So let's say this is W11. So to find the gradient of loss with respect to W11, I'll need to back propagate. I'll first need to find gradient of or partial derivative of loss with respect to y multiplied by partial derivative of y with respect to a1 multiplied by partial derivative of a1 with respect to z1 multiplied by partial derivative of z1 with respect to w11. That's it. This is exactly what I've written in mathematical formula here. The partial derivative of the loss with respect to W11 is equal to the partial derivative of the loss with respect to y multiplied by the partial derivative of y uh, with respect to a1 multiplied by the partial derivative of a1 with respect to z1, which is here, multiplied by the partial derivative of z1 with respect to w11. So this is the chain rule in action. And once I take the product of these four terms, I'll get the partial derivative of loss with respect to W11. Now let me go ahead and find each of these quantities here. And for that, the notation will be very useful, which I mentioned before. So let's look at the partial derivative of L with respect to Y. Remember, loss, which is L, is just Y square. So the partial derivative of L with respect to Y is equal to 2Y. Then y is equal to a1 plus a2 plus a3. So partial derivative of y with respect to a1 is just equal to 1. Then partial derivative of a1 with respect to z1. Remember, a1 is ReLU of z1, and for a ReLU function which looks like this, if we are on this side, which means if z1 is greater than 0, the derivative will be 1. If we are on this side, the derivative will be 0. So partial derivative of a1 with respect to z1 is 1 if z1 is greater than 0. And then finally, partial derivative of z1 with respect to w11. So if you look at z1, z1 is w11 x1 plus w12 x2 plus w13 x3 plus w14 x4 plus b1. So partial derivative of z1 with respect to w11 will just be equal to x1 here. And that's exactly what I have written here. So when we find the partial derivative of loss with respect to W11, we will just take the product of these four terms. So then partial derivative of loss with respect to W11 will be 2y multiplied by 1 multiplied by 1 if z1 is greater than 0 and multiplied by x1. Okay. Similarly, partial derivative of L with respect to W12 will also be equal to 2y into 1 if z1 is greater than 0 multiplied by x2. Remember, for W12, which is the weight coming into this neuron from this particular input, the only thing which will change is that we will need to take derivative of z1 with respect to W12. So only x2 will survive. So in the formula, the answer for the derivative of L with respect to W12 is very same as W11, except that instead of x1 it will be x2. Similarly, partial derivative of L with respect to W13 is 2y multiplied by 1 if z1 is greater than 0 multiplied by x3. And partial derivative of L with respect to W14 is 2y into 1 if z1 greater than 0 multiplied by x4. It's very simple to calculate each of these partial derivatives if you have written the notation correctly. Now let me do one iteration of the forward pass and calculate y, calculate z1, and then multiply to get the derivatives. Okay. So I'm going to use these values. I'm going to use W1 as 0.1, 0.2, 0.3, 0.4. W2, which is the second weight matrix. So this is the first weight matrix. So each of these, so this is W11, this is W12, this is W13, and this is W14. Similarly, this is W21, W22, W23, W24, and this is W31, W32, W33, and W34. And this is my B1, B2, B3, which are the biases of the three neurons. And my inputs, which are feeding here, x1, x2, x3, and x4, they are fixed. So they are 1, 2, 3, and 4. These are the values which I'm starting with. Okay. So let's do one iteration of the forward pass actually. And let's try to find out what each of these values are. So when you do the forward pass, you will calculate Z1, Z2, and Z3 through these summations. And it turns out that Z1 is equal to 3, Z2 is equal to 7.2, and Z3 is equal to 11.4. So immediately Z1 is greater than 0. So this will be just 1. So the gradient of L with respect to W11 will be just 2y multiplied by x1. Gradient of L with respect to W12 will be just 2y multiplied by x2. Gradient of L with respect to W13 will be just 2y multiplied by x3. And gradient of L with respect to W14 will be 2y multiplied by x4. So we need to calculate the value of y. Okay, so Z1 is 3, Z2 is 7.2, and Z3 is 11.4. Remember, to get A1, A2, and A3, we just apply ReLU. And all of these are greater than 0. So ReLU will be just equal to the values of the Z. So A1 will be equal to Z1, which is 3. A2 will be equal to Z2, which is 7.2. And A3 will be equal to Z3, which is 11.4. And Y is equal to A1 plus A2 plus A3, which is 21.6. And the initial loss is Y square, which is 466.56. This is one iteration of the forward pass. Okay. Now, as we calculated here, gradient of L with or partial derivative of L with respect to W11 will just be 2y into x1. I have just written it here again for reference. So partial derivative of L with respect to W11 will be 2y into x1. Since y is 21.6, this will be 43.2, the partial derivative. Partial derivative of L with respect to W12 will be 2y into x2, which is 86.4. Partial derivative of L with respect to W13 will be 2y into x3, which is 129.6. And partial derivative of L with respect to W14 will be 2y into x4, which is 172.8. So we have calculated these four partial derivatives of the weights belonging to the first neuron, which are these weights. Now we have to calculate the partial derivative of loss with respect to the weights belonging to second neuron, which are W21, W22, W23, and W24. So let's go ahead and calculate those. Very similar to this back propagation which we did, we will find that the partial derivative of L with respect to W21 will be just equal to 2y multiplied by x1, because since z2 is also greater than 0, this term will also become 1. So the only thing which will survive is again the inputs x1, x2, x3 or x4. So it turns out partial derivative of L with respect to W21 is also 2y into x1, and in fact partial derivative of L with respect to W31 is also 2y into x1. And this is the same for partial derivative of L with respect to W22, that's 2y into x2, which is same as what we calculated for W12, and that's the same for W32. And it's similar for W23 and W33 and W24 and W34. In short, partial derivative with respect to W11, 21 and 31 are identical, and that value is 43.2. Partial derivative of loss with respect to W12, W22 and W32 are identical, and that value is 86.4. Partial value of loss with respect to W13, W23 and W33 are identical. That value is 129.6. And partial derivative of loss with respect to W14, W24 and W34 are identical, and that value is 172.8. So this is the partial derivative with respect to 12, the partial derivative with respect to 12 weights. But remember, we also have biases, so three more parameters are remaining. So now let us calculate the partial derivative of loss with respect to the biases. So with respect to the first bias, it will turn out, let's look at it from the diagram. Partial derivative of loss with respect to A with respect to partial derivative of loss with respect to y multiplied by loss with respect to a1 multiplied by a1 with respect to z1 and multiplied by z1 with respect to b1. And remember, partial derivative of z1 with respect to b1 is equal to 1. So only thing which will survive is 2y into partial derivative of y with respect to a1, which is anyway 1. So it turns out partial derivative of L with respect to B1 is 2y, of L with respect to B2 is 2y, of L with respect to B3 is 2y. So partial derivative of loss with respect to all the bias terms is equal, and that's given by 43.2. That's great. Now we have the partial derivatives with respect to all the 15 parameters which has been computed over here. And now we are ready to do the first update of the gradient descent, right? So the way we are going to update the gradient descent is that we are going to subtract by the learning rate multiplied by the partial derivative of the loss with respect to that weight. So the new value of W11, the new value will be the old value uh, minus 0.001, which is the step size, multiplied by the partial derivative of loss with respect to W11. So it turns out that the updated value for W11 is 0.0568. Similarly, we can get the updated values for all the other weights and all the other biases which have been mentioned in this box here. We do the exact same rule as has been written here. So for example, if you see W34, the updated value of W34 is the original value of W34 minus the step size into the partial derivative of loss with respect to W34. And we have already calculated the partial derivatives above. So then it's very easy to get all these 15 updated values of the weights and the biases. Once we have the updated values, we can do a forward pass again and check to see the new loss value and is it less than the original loss. So the original loss was 466.56, right? Now let us look at the new loss value. Okay. When you find Z1, Z2, Z1, Z2, Z3 and A1, A2, A3 for these updated values of weights and biases, it turns out that A1 is 1.76, A2 is 5.86 and A3 is 9.96. So Y, which is equal to A1 plus A2 plus A3, will be equal to 17.5824. So the loss, which is just Y square, will be equal to 309.14. This is the new loss which you obtain, and the original loss value was 466.56. So just in one iteration of gradient descent, we were able to reduce the loss by around 150. That's amazing, right? I hope you are able to see that back propagation is not difficult. It was not difficult for a neuron, and it was not difficult for a layer of neurons also. We just need to make sure that the notations like the Z notation, the A notation, the Y notation is written correctly. And once we have this visual map, right, of where the information is flowing, we can just compute the gradient by doing these back propagation passes like this. So if you want to find the gradient of loss with respect to W11, visually you should be able to see that it will be the product of four terms. Partial derivative of loss with respect to y multiplied by partial derivative of y with respect to a1 multiplied by partial derivative of a1 with respect to z1 and multiplied by partial derivative of z1 with respect to w11. That's why it's called back propagation. Okay, so we have done one iteration of gradient descent and the loss is minimized, or loss is rather reduced, but it's still not optimum because the loss is pretty high. So for that we'll need to do a large number of iterations of gradient descent. And right now, since it's difficult to do all those iterations on a piece of paper, I'm again going to take you to Python code to show you how easy it is to write this code of the backward propagation in Python. So I'm just going to increase the zoom in here. Okay, so now we have zoomed in a bit here, and I'm going to now show you how to do a backward pass through a layer. So first we have the inputs, which is 1, 2, 3, and 4, and then we have the weights. So as we have the weight values determined here, the weights of the first neuron will be zero point 0.1, zero point 0.2, zero point 0.3, zero point 0.4. Second neuron will be zero point 0.5, zero point 0.6, zero point 0.7, zero point 0.8, and third neuron will be 0.9, 1, 1.1, and 1.2. This is exactly what has been written over here. These are the weights. The first row are the weights of the first neuron, second row are the weights of the second neuron, and third row are the weights of the third neuron. And here are the three biases: zero point 0.1, zero point 0.2, and zero point 0.3. So the learning rate which we have obtained here is 0.001, which we are going to use because it's a practical small rate which is generally used. And then we just need to define two functions. We define ReLU, which is maximum of 0 comma x, and we define the derivative of ReLU, which is 1 when x is greater than 0, and if it's 0 otherwise. So it's important to note that there is this np.where function. So what this does is wherever x is greater than 0, the value is 1, otherwise it is 0. It's useful to know about this function as well. The reason we calculated these two functions is because this third term, right, gradient or partial derivative of a1 uh, with respect to z1, this term, that is basically the derivative of the ReLU. Okay, now we will do forward and the backward passes. So first we calculate the forward pass. So the z is just the dot product of weights, inputs, and then we add the biases. Then we take the ReLU of all the output, and then we do the sum, and then the loss is y square. So these four steps which have been described in the code, they are exactly the steps which we discussed over here. First you find z1, z2, z3, then you find a1, a2, a3, then you do a1 plus a2 plus a3, and the loss is a1 plus a2 plus a3 whole square. Now we will be doing the procedure of backward pass. Remember that in the backward pass we actually need the following quantities. We need 2y, we need the ReLU derivative, and we need the inputs x1, x2, x3, and x4, and we just need to multiply these quantities. That's exactly what's done here. First you compute the 2y, which is the gradient or the partial derivative of loss with respect to y. Then there is this ReLU derivative term here, and essentially you are multiplying this term, which is 2y multiplied by a vector of ones multiplied by the ReLU derivative. So essentially, when you do the gradient or the partial derivatives, what you will have is just the product of these terms 2y into 1 into ReLU derivative multiplied by the input x1, x2, x3, or x4. Okay, so yes, okay. So see, this last term which is inputs here is this last multiplication term, partial derivative of z1 with respect to w11, etc. So essentially what is done in this part of the code, this backward pass, is just we are computing those different partial derivatives and multiplying them with each other. And remember, when we do the partial derivative with respect to the bias, we don't need to do the multiplication with these inputs, because the partial derivative with respect to bias is just 2i into 1. So then this x1 term does not need to be there. And so that's the reason why we don't take this dot product which we do for the partial derivative with respect to the weights. Once we have computed the partial derivative, we will just update the weights and biases. So the new weights will be the original weights minus learning rate into partial derivative of loss with respect to W. And the new biases will be the original biases minus the learning rate multiplied by the partial derivative of loss with respect to B. This is exactly what we had shown in the gradient descent step sizes or in the gradient descent updates. So now what I'll be doing is that I'll actually be just running for two iterations and I'll be showing you the loss. So I'll print out the loss after every iteration. So let me just run this code here. I think it's still running for 200. So let me again run this code. Uh, Great. So the first loss was 466.56 and the second loss was 309.14. Let's see what we had obtained. Our first loss was 466.56, so that's correct. That is matching what's there in the code. But the more important is the second loss. So second loss is 309.14, and here also it is 309.14. Great. So what we had calculated on the whiteboard for the second loss is matching the code second loss. So we can proceed and go ahead with the code. If I did 200 iterations on this piece of whiteboard, I had also have reached the minimum loss, which is close to zero, and the optimal weights and biases. But it would take a long time. So what I'm going to do is just I'm going to run this for 200 iterations, and I'm going to print out the loss after every 20 iterations. So let's see the updated loss and the final weights and biases. So look at the loss at iteration 180. The loss is 6 into 10 raised to minus 9, which means the loss is almost zero. And now our neural network is trained, which means that we have the weights and the biases which minimize the loss. These are the 12 weights and these are the 3 biases which minimize the loss, or these are the weights and biases for which the output of this neural network with 3 neurons is closer to 0, which was the true value. So now using backpropagation through a layer of neurons, we have computed the optimal values of weights and the biases which would minimize the loss. What we did right now is exactly what is done for a group of layers as well. So if you look at large neural networks, it's just that more backpropagation passes happen. So right now we just looked at one hidden layer, right? If we have multiple hidden layers, there will be more backpropagation passes which happen. But the underlying logic is simple. You just chain these different passes together and take a product of these partial derivatives. Similar to the product which we took in the backward pass right now. And based on these products, we get the partial derivative of loss with respect to weights and biases. And then we update the weights and biases. And we then do it for multiple times. Right now, we are using simple gradient descent. But later, we'll be learning about more complex methods like stochastic gradient descent, ADA-grad, ADA-delta, ADAM, etc., which are adaptive step sizes. Right now, the step size is fixed, but we will come to that a bit later. The main purpose of this lecture and the previous one on backpropagation is so that you are not scared of backpropagation. It is not a very complicated concept. If you just understand the chain rule, and I also have a lecture on chain rule in this series, then you are in a very good position to understand backpropagation. I would just encourage you to write this on a piece of paper or on a whiteboard format like I'm doing. Once you do these product of partial derivatives on your own, you will never forget backpropagation. In fact, neural networks will start seeming easier to you and not just rocket science or magic. I wish it was taught to me like this when I was in school or college. Thank you so much, everyone, and I look forward to seeing you in the next lecture of the Neural Networks from Scratch series.